Alright, so in the last couple of videos, we talked about two different subsets of R2, and we asked whether or not there are subspaces of R2. So we worked through all of the algebra and definitions to show that W, all xy pairs such that 7x plus 5y was 0, that was a subspace, and that on the other hand, the subset of R2 where x cubed plus 7y is equal to 0 was not a subspace, right? And so we did this, and we can verify that it fails some of the properties, but it helps to understand beyond the algebra, geometrically, what's going on. Why is one of these things considered a subspace and the other one not? And so, because we're in R2, this is a relatively nice vector space we're working in. It's just a two-dimensional standard Cartesian plane. So we can actually plot these things out and graph them and get some intuition as to what is it exactly that makes one of these things a subspace and one of them not. So let's go ahead and plot these two values out. One of these was 7x plus 5y equals 0. And let's make that green. And so that's that curve there, which is not a curve, it's just a straight line, right? And of course you could actually just solve for y and get the mx plus b expression of this line. And let's go ahead and plot the other one, which is x cubed plus 7y is equal to 0, which gives us this curve here. Let's make that red, which is our other set, right? And again, in both these cases, the plots of these lines shouldn't be too surprising. You can just solve for y and you get the appropriate polynomial, and these are the respective graphs. So let's just take a look at W here. So W, we're claiming, is a subspace. And so let's take a point on this subspace. Let's say when x is with something nice. When x is 1, maybe y would have to be minus 7/5. Right? So that's this point here. And let's do this. Let's make that dotted. Let's actually make a table with the origin and so the vector 1 comma minus 7/5 is this vector here. So what we can see is that this vector here lies within this space. And so if I were to pick another vector that laid on this space, let's say when x is minus 2, then we can think about what y would have to be. It would have to be minus 14/5. Sorry, 14/5 positive because of the negative. Then that vector here, likewise, also falls on that space, right? And if I were to add the two vectors together, then that creates this third vector here, which is still in the space, right? Since they all lie on the same line, if I add together things on this line, I'm only going in the one direction or the other, right? And so adding together different things on this line will keep them on this line. And then as far as scalar multiplication goes, let's just see what's going on here. As far as scalar multiplication goes, if I take one of my vectors and I multiply it by a scalar, that's always going to lie on the line, right? Now, you have to still verify all of these things with the algebra, but the algebra we did in the other video is just confirming what our geometric intuition tells us here. Alright, so let's talk about u then. U was x cubed plus 7y equals 0, which was a cubic, right? And so when we talk about what goes on Q, or on U rather, let's now pick a vector on this curve. Let's say when x is 1, y is minus 1/7. If we zoom in a bit, we can see that that curve definitely lies in U, right? That this vector is a vector in U. But the problem is that now if I add it to itself, that this point here, 2 minus 2/7, it does not lie on U, right? We've taken a vector in U, added it to itself, which is a vector in U, and we will obtain a vector not in U. So by doing this, we can see that the vector addition on this set is not closed under addition. I can take two things in U, add them together, and get something not in U. Let's take another example here. Let's say 0.5 get rid of that. Let's say 0.5, and when x is 0.5, y is minus 7th. Minus minus 7 times 8, that's this here, right? From 0 to minus 7/8. If I now add 1 plus 0.5 and minus 1/7 plus minus 1 over 7 times 8. That's this vector here, which is once again not in U. And so that addresses the issue of vector addition, right? Which is enough to show that this is not a subspace. On the other hand, we can also show that it doesn't respect scalars either. So we know that 1 comma minus 1/7 was in U. But in order to be a vector space, every multiple of that vector should also be in U. And what we note is that, alright, so when I take minus 1 times that vector, that's in U. 1 times that vector, that's in U. That's all fine. But pretty much every other, and 0 times that vector is still in U, which is great. But for every other value, those vectors that you obtain from scaling by other constants, they're not in U. So this subset also fails the rules of the scalar product. And so it's because of either one of these things failing, we have that this set is not a subspace of R squared. And hopefully that gives you some idea of what type of things need to happen or need to be true in order for uh, a space to be a, or a set to be a subspace. All right, thank you.